the fall version, which is, of course, being done on, we spread it out since we aren't all meeting, so there's no point in us trying to do it all on a Saturday. And of course, I have already forgotten the calendar. Randy, do you remember which the next day was?
2 weeks from now. It's every 2 weeks.
Every 2 weeks. Okay, that's easy to remember, supposedly. So every 2 weeks. And so it's a pleasure to start this this semester off with Simon Cho. He's at the University of Michigan, and he'll be talking to us about parameters in index homology. Simon.
Thanks for the introduction. Let me just start by sharing my screen. Okay, can everybody see this?
Yes.
Okay, great. Yeah, thanks for the introduction. So this work was done while I was at University of Michigan, but I'm no longer there. So I just wanted to clear that up. So yeah, and of course, I guess I should thank the organizers for not only inviting me to speak, but having to deal with the kinds of emergent circumstances that they've apparently obviously had to deal with. So yeah, I mean, yeah, that's you guys probably dealt with a lot of difficulty. So thank you for that. All right. So I'm going to talk about something that came up as a result of wondering what the connection between persistent homology and magnitude homology is, right? So there are two things that kind of feel like they should be related, but for me, it wasn't very clear how to say they're connected, right? So this project was kind of an attempt to answer that. Yeah, sorry. Okay. Right, so a brief outline. I'll start by talking, giving a brief introduction to persistent homology. I wasn't sure how much I should assume people were familiar with this. I noticed, at least a few people here who know quite a bit more about persistent homology than I do. So at the same time, this is going to be recorded and it's, I think, public. So I figured it warrants at least some brief introduction. And I'll do the same for magnitude homology. For those who already know a lot about these topics, I ask for and appreciate your patience. And then I'll talk a little bit about LP norms or LP sums and how they kind of hint at what the connection should be. And then using that as motivation, I'll get into the kind of the theory, right? The underlying theory. So I start developing it in order to find out what the connection is. And then kind of one payoff of that is not only to explain why these two things should be natural things to look at, right? But the other payoff is that, it suggests some natural ways to apply these tools further, right? Okay. Okay, so persistent homology, right? So here's a typical use case or a toy example of a typical use case, right? So you have some data, it might be image data, it might have some noise, right? And you have what appears to be roughly a circle shape, right? And you want to be able to say, right? There's formalize that mathematically, right? So that's what persistent homology does, right? So you have this circle going through the data, and it detects large scale features by ignoring kind of small scale noise, right? And the machinery just produces for each choice of natural number n and real non-negative real number r a vector space whose dimension is just the number of n-dimensional holes at that length scale, right? So like ignoring stuff that's that occurs at distance below distance r. Okay. So this is built upon, this is obtained by a construction called the Vietoris-Rips complex. Okay, that's kind of the main ingredient in persistent homology, right? And so you have a metric space X, right? And we call that VR of X. And it's, for those of us who haven't seen like the simplicial complexes or whatever, you can think of it as essentially a hierarchical clustering of X, right? And it's parameterized by two things. So number one, how many points you're forcing to be in each cluster, right? So that's n, it's a whole number. And how far you're allowing points to be in a particular cluster, right? So that's the length scale R, right? It has some extra structure and extra data in it. Like for example, clusters can overlap through smaller clusters, right? And so for those of us who have seen this, right, of course, each cluster is just a simplex, right? And like overlap, you're allowed to have like repeats of points, but they should kind of behave well in some sense, okay? So in a bit more detail, right? So for each fixed whole number n and real number r, you're looking at a tuple of n+1 points, right? And so that's called this n simplex at scale r when it satisfies this condition on the distances between its points, right? So its pairwise distances are all bounded above by r, right? So that's an n simplex. And if you have two real numbers r and s, right? Well, if a tuple of points satisfies this condition, right? Can you see me when I use the cursor to point anything?
Yeah.
Okay.
Yes.
Great. So if you have a tuple of points that satisfies this distance for r and s is greater than r, then of course, right, it's clear that that's also a simplex at scale s. So there's natural inclusion. And in the parameter n, it satisfies what are called the simplicial identities. Just means that if you fix r, right, and you range over all of n, it behaves like a simplicial complex, if you will. It's just saying that it kind of behaves nicely geometrically. Okay. And so if you apply homology pointwise, right, along R, then you get the vector space that I talked about just now. Okay. Okay. So what it does is it takes this kind of circle here that you want to be able to talk about formally, right, and then at small values of R, right, it starts filling in these kind of simplices, and so this is H1, right? So you see these kind of one-dimensional holes popping up, right? And the smaller holes have already been filled in at the scale, right? And so each kind of qualitatively different loop you see corresponds to a generator of H1 at this length scale, right? So this is, right, these are images that I've pilfered from like various sources. And so this kind of barcode, right, is a kind of typical way that people use persistent homology to represent data, right? So if you look at the longer barcodes, means that like these loops, these large scale features, or these features of the data persist over longer ranges of length scales, which means that they're more significant, right? So you can see that this really long barcode should be the one that corresponds to this kind of very large feature. Okay. Are there any questions about persistent homology?
I guess could you say a couple of words about how you identify the loop at one radius with the loop at another radius?
Yeah. So I mean that's something that would be done at the computational stage, but to determine like, right. So if you start kind of increasing the radius, right, some loops kind of, you might have like two loops that merge together, right, to form one big loop, right? And so or maybe some loops die off, right? So the way you determine like which generators, in this barcode representation survive is something called the elder rule. It just means that you keep the one that was born before, right? And so that's kind of what makes it possible for us to be like, hey, this survived for a longer period of time and it's more significant. Yeah. Cool. Okay, so magnitude homology. So whereas persistent homology is kind of, you detect large scale features, large scale holes that's insensitive to small scale noise, magnitude homology is used for different purposes, right? So you can consider it as an obstruction to convexity. I think there's at least one group in the Japanese mathematical community that uses it to study like curvature properties of metric spaces. It's like pretty interesting, but I don't know that much about it. You can also think of it as detecting like kinks in a space. I can say a little bit about that in a few seconds. So here, right, for each, the main result is that for each length scale R, right, the first magnitude homology group at that scale has one basis vector for each pair of points, right, for which, well, the distance between them is exactly R, and there are no points that are strictly in between them in terms of distance. Okay, so that's what this means, right? So this is, there does not exist a point for which there's like it lies on like the metric straight line segment between them, right? So yeah, you take a metric, magnitude homology.
Sorry.
Yeah.
I'm sorry, I don't understand. So you're telling me that then you don't have a vector in you don't have an element in the space? I mean, suppose there were a point X that were between 2 points A and B that were R apart. Then then the pair AB wouldn't be part of the group?
Yeah, exactly. So this
So you would just throw it out, even though it is R apart. You throw it out because it's as if it's actually two legs in a walk that is a straight line.
I mean, you throw it out because there's something in between them. Yeah. So the generators are like pairs of points that are kind of like length primitive in a sense.
Got it. Like they're like basis lengths. Okay.
Yeah.
All right. Thank you.
Mm-hmm. Right. So you have magnitude homology is obtained by a construction called the magnitude complex, right? Well, actually, I think I might be the only one who calls it that, but whatever. Yeah. So X is a metric space, right? And you call it what I call the magnitude complex. It keeps track of paths through tuples of points and kind of their relationships to paths through subtuples of points, right? And the idea is that you measure lengths of paths going through those tuples of points, right? And then you look at what happens if you take out kind of the intermediate points in those tuples, right? And if the lengths get shorter, then you know that the original path wasn't like a straight line segment to begin with. Okay. Or rather, the intermediate points that you took out wasn't on the straight line segment. Yeah. Okay, so how do you actually construct this? Well, for each n and r, a tuple is a simplex, right, of the magnitude complex if it satisfies this requirement, right? So if the sum of their successive distances is less than or equal to r, right? So there's one thing that we need to do that I call localizing. It's not the same. So this is kind of an etymological sin on my part, but it's kind of the only appropriate name I could come up with because it does not coincide with the homotopy theoretic usage of the word localization, but it is appropriate in this sense. So I'll explain what that means a bit later. But you localize this, and then you apply homology pointwise along R, right? And then you get the magnitude homology groups. Okay. Okay, so we can already kind of notice, we can already kind of smell that something should be, like, there's a connection here, right? I mean, okay, aside from the fact that they're both about like metric spaces, right? And the lengths between like tuples of points, right? Like these conditions for simplices to be a part of the complex, you know, they're kind of formally or thematically similar, right? But to make that precise, right? You need to kind of dive in a little bit more, right? And this is where kind of developing the underlying theory actually helps you see it clearer. But as a spoiler, right? Here's what you come up with to make the connection a bit more explicit, right? So on the left-hand side, right, this condition actually turns out to be equivalent to this, right? And this equivalence is just by nature of what taking the maximum does, right? You just take all of these to be the same, right? Just take these to be R, right? Here, like, I mean, I think it's clear that the bottom is like a priori stronger than the top, but the top is also implies this. Wait. The harder direction is implied by the fact that by nature of what taking the max is, okay? On the right-hand side, the equivalence results for a completely different reason. The reason is that in a metric space, the triangle inequality holds, okay? So, yeah, they're equivalent for like unrelated reasons, which actually kind of confused me for a while when I was trying to suss out what the connection was. Okay. So once we get to this point, how can we kind of, well, this is very suggestive of what we should do next, right?
I have a question, if that's okay.
Yeah.
For those of us who've never seen magnitude homology, do you have a nice picture like the circle that you had for persistent homology?
I looked, and I couldn't, there aren't as many pictures of magnitude homology as, yeah. There were some pictures in some papers that proved results about magnitude homology, but they were pictures about those proofs, and in my opinion, not very illustrative of like how one might want to apply it, right? But yeah, I apologize. So we have these kind of like very formally similar things, right? And so this suggests that we should be like, okay, well, let's look at the LP norm, right? Because if you take the max of a bunch of numbers, that's the L infinity norm. If you take a bunch of, if you take the sum, that's the L1 norm, right? So we're just thinking of these numbers as being the components of a vector, and just take the LP norm of it, right? And so you can actually just say, okay, well, the condition on the left is just this thing with p equals infinity, and the condition on the right is the same, except with p equals 1. Okay, well, that alone isn't enough to kind of say, okay, well, they're connected, there's a coherent theory, right? Like, we need to kind of say, okay, well, let's use this as a hint to kind of flesh out why these things are like natural to begin with, okay? So have I said everything that I wanted to? Yeah. So a brief interlude about monoidal structures, right? So we can think about the LP norm as, or the LP sum as a monoidal structure on the non-negative real numbers, right? Because it's unital and associative, right? And then if you equipped, so for any choice of P, right? The non-negative real numbers equipped with the LP sum is a quantile, right? And for it, like it's order reversing, right, in this sense. So if P is less than or equal to Q, right, then the LP sum is greater than or equal to the LQ sum. And we think of each P as giving a different way that like distances or paths compose, right? I can say a bit more about that going forward. I should also mention, for those of you who are familiar with quantals, it's actually more natural categorically to think of these things with the opposite ordering from the usual. So, you know, in my paper and elsewhere, right, like this is written as R op to make it coincide with the usual ordering. So, but you know, I didn't want to have to clutter everything with like op everywhere. So I just kind of just keep in mind that like I'll sometimes say things that are exactly the opposite of what I mean. Okay. So so here at this point, we're really going to start to kind of delve into fleshing out a categorical, what I think of as like a categorical semantics of persistent and magnitude homology, right? So here's a bit of the motivation or the story in the about the direction we're going to take in order to do that. So given a space, right, you can take its nerve, right, and carries all the things that you might care about if you're a topologist. So the slogan is that the sensible notion of nerve, right, it encodes the important spatial features of X, right? And then you could do a lot of things with it. Like, for example, take homology of it, right? I mean, there's a lot more you could do with it, but yeah, I mean, one of the things is take homology, right? And so the punchline that we're going to get to in a little while is that there's a single kind of fundamental nerve construction that's parameterized by a real number, P, right? The same one that we saw in the LP sum, right? And when P equals infinity, this gives the Vietoris-Rips complex, and when P equals 1, it gives the magnitude complex. Right, so when I say nerve, I just mean this general notion of you have a bunch of test spaces, right? These n simplices that you're probing your space with, right? And so all the different ways you could probe the space with your like specified collection of test spaces forms the data of your nerve, right? And in this case, in our case, right, the Vietoris-Rips complex already encodes enough information to completely reconstruct the space at like n equals 1, right? So why should we care about like the higher ends like we do? Well, the nerve isn't just a way to encode important information about your space. It's also a way to organize that information in a way that lends itself to kind of extracting nice features about the space, in this case, like higher order kind of distance interactions, right? So, okay. So we can imagine, right, a metric space that doesn't have any right to be called a metric space, right? It's actually just what we might call an R graph, right? So that's just a graph, right? It's a set of points or vertices, right? And each pair of vertices is equipped with a non-negative real number value representing its distance. But you know, it might not obey any of the rules that for metric spaces that we're familiar with. It doesn't even have to be symmetric, for example. Okay. Also, a bit of notational. As a bit of a point about notation, I tried to be as consistent as possible about including the greater than or equal to 0 part whenever I use R, but some of the slides are cluttered enough as it is, so that for like R graphs and the category of R graphs, I just omit it. But whenever I talk about R, you should keep in mind that I'm talking about the non-negative reals. And whenever I say the real numbers, like, yeah, similarly. Okay. So if you have two R graphs, X and Y, right, a morphism between them is just a one Lipschitz map, right, a distance non-increasing map. It makes sense even if they don't apply, obey the metric space axioms, right? And then the category of such is just R graph. Okay? And then if you choose a value of P, right, which we said kind of specifies a rule for how distances should compose, right? Then you can ask, okay, well, in a given R graph, do the distances compose nicely, right? So this first, so an R graph X is called an LP metric space, right? When it obeys this kind of very sensible first rule, right? A point should have zero distance from itself. And the second rule is that it obeys like the LP triangle inequality, right? So, I mean, that's exactly what this is, right? So when P equals 1, this is exactly the usual triangle inequality. And so L1 metric spaces are just the usual metric spaces, modulo a few details like symmetry. So this generalization actually gives us a cleaner and more natural theory, and then we can specialize later on to whatever we're interested in. Okay, and for those of you who are familiar, what we call LP metric spaces are just like R comma P categories. Okay. So if you have two LP metric spaces, right, a morphism between them is just a morphism between them as R graphs. Okay. So that automatically includes the category of LP metric spaces as a full subcategory of R graph. And also notice, because of our LP sum inequality, right, for different choices of P, if it satisfies the LP triangle inequality, then it certainly satisfies the LQ triangle inequality. So we have an inclusion of categories. Are there any questions so far? And so, right, for any kind of two choices of P, right, so for P and Q, you might have this like a triangle, commuting triangle of inclusions of categories. It turns out that these are all right adjoints, right? And so they have left adjoints, which are kind of like the free, I mean, they're free constructions, right? So all these Fs just all make the minimal modification that you need in order to turn it into like an LP metric space or an LQ metric space, right? And it's not too hard to like write down explicitly what it does to any given metrics R graph, but we'll see what it does to a certain kind of space that we're interested in, our test spaces that we're going to construct the nerve with. Okay, so we're going to construct our test spaces, right? So for any right n, right, and any tuple of real numbers for our distances, we just connect all of them head to tail, right? And we just make the R graph out of it, right? So it has n plus 1 points, right? X0 through xn, and the distances between them are just this, right? I mean, and like from the perspective of a classical like metric spaces, right? This is a very pathological space. It's not a metric space, right? So we think of this as the n spine, right, with these lengths, right? So wherever you don't see like an arrow, it means that the distance is infinite. Okay. Now, if you pick a value for P, right? So, I mean, why does this fail to be like an LP metric space for any P? Well, the distances don't compose well, right? And so you can ask, okay, what would it mean for it to compose well? Well, you just make the minimal modification, right, to it to make the distances compose well for a given chosen value of P, right? So this is the simplex parameterized by those lengths, right? And the explicit description of the free construction on this gamma right? So you take you apply the free construction on the R graph, and then you just include it back, right? And that's what this is. Right? Okay, so as an explicit example of what happens to this 3 spine with lengths R, S, and T, once you apply like IF to it, right, it fills in the distances by just composing everything that you can, right? And it doesn't make them any shorter than it needs to be, right? So if P were 1, for example, like x0, x1, x2, x3, they would actually be in like a straight line, metrically speaking. Okay. So if you now take 2 such tuples of lengths, right? Well, and each component right here is greater than each component, the corresponding component on the left, then you get the reverse direction, a map in the reverse direction. So we get a functor this way if we set the values on each tuple of lengths to be this, right? It's the Hom set. It's now we're just doing exactly you know what you do for nerves in general, right? You're probing your space X with your test spaces, right? But now instead of like just having like an n's worth of test spaces, you have an n's worth of test spaces, but for each n you have like all possible real number tuples of length n, right? So that's this set of n simplices that you get, right? For a, yeah. Any questions so far?
Yeah, I have one question. There's something about your spines that feels very reminiscent of the directed homology that, for instance, Catherine Hess and her collaborators have been looking at. Do you have any idea whether there is a direct connection there?
Well, the answer has to be no, because I don't know. I don't know what work you're referring to, but I would be very interested in checking it out later. So, yeah, I mean, I think in general, like this kind of like spine-like construction and then like filling it in using free constructions is like a pretty this theme is like pretty widely spread, I think, in uses of algebraic topology. But I mean, other than that, I'm not sure I have a satisfactory answer to that question. Sorry. Okay, so yeah, so the choice of P determines, right, what these simplices kind of look like. Now, one kind of technical problem that arises is that for each, in like the classical, let me go back to the classical. In the classical case, right, there's no lengths to worry about, right? So it's fine, but here, right, if you change n, right, this, like the space that you're kind of like probing out of changes, or the category that you're probing out of changes, right? And so what you end up doing in order to kind of resolve this is, well, for any tuple, right, you can all just mash them together using the p-sum, right, LP sum, right? And you just take the nerve for each fixed n, you just left con extend it across the LP addition, right? And so that's the nerve functor that we want, right? So for each value of R, right, now you get this condition for it to be an n simplex at scale R. Notice this is exactly the condition that we saw that qualified a tuple to be a simplex of either the persistent, either the Vietoris-Rips complex or the magnitude complex, depending on what P was. The point I want to emphasize is that like these are all kind of like very natural beginnings and operations for what people might want to do in topology. Okay, and of course, right, like we were just talking about the natural numbers, but the tuples all kind of very like manifestly behave in the ways that you would need them to in order for them to assemble like simplically, right? So it's not just right, it's not just like a collection of things that you have for each n. They assemble into a functor out of the simplex category, right? So this is the same thing as a functor from the real numbers into the category of simplicial sets. You could think of simplicial sets as just nice, simple, well, okay. Geometrically, they can be terrible simplicial complexes, but theoretically, they have very nice properties, right? So the category, this is the category of simplicial sets, and now you have an honest kind of indexed simplicial set, right, for each x, right? And remember, we're humming into each space x, so this is evidently natural in x, right? So now you have a functor from the category of R graphs into R indexed simplicial sets, right? So this is what we call the LP complex, right? And so the L1 complex is just the magnitude complex, and the L infinity complex is just the Vietoris-Rips. Okay. Yeah, and so that I guess that's exactly what this is. Okay. Also notice that for any value of P, right, there's a natural transformation, in fact, an inclusion, right, from the LP complex into the Vietoris-Rips complex. Okay, and now it's time for me to make good on the promise that to explain what I meant by localization, right? So at this point, right, if you just took the L infinity complex and applied homology pointwise along this R, right, that's just persistent homology, right? And then you might say, okay, well, let P equals 1 and then take homology. Well, that's not magnitude homology, right? You have to localize first. And so now I'm going to explain what I mean by that. Okay, so for magnitude homology, what we do is, let me go back to this. So remember, this isn't a condition where this is less than or equal to R. It has to be exactly equal to R, right? So you're actually killing off all the information that's below, strictly below R. And so what you do is you take the magnitude complex and its value at each real number R, and you just mod it out by, you know, the value of the magnitude complex at every value below R. Now, strictly speaking, right, we're actually talking about this happening at the chain complex level instead of the simplicial set, because simplicial sets don't have an algebraic structure a priori, right? Like you turn it into a chain complex, and then now that's what you're doing here. Okay. So one kind of way to put this on more solid abstract footing is take a map, a functor, right, from the real numbers into the category of intervals of real numbers, intervals containing 0 of real numbers. For example, right, this is one such choice of J. Right? You take each real number and then you just return this interval, right? Then this transformation we just saw, right, is just this, right? You say for each at each value of R, or each value of the magnitude complex at R, you just mod out by all of the things that are contained in J of R. Right? So this is sort of the maximal choice of J that you can make while still retaining all of the information about your original space, right? Because what you're doing is like, you're just killing off like everything that came before, right? But it actually, I mean, this construction is like more general, right? You could have chosen some other J. For example, you could have chosen the minimal J where you return the empty set for each R, right? In which case localization doesn't do anything, and it just gives you the original complex back, right? But you could have something in between, right? You could say, okay, well, for a real number epsilon, let's say some small real number epsilon, for each R, return the interval from 0 to R minus epsilon, right? And that's like a perfectly fine choice of J, right? And so in that case, like, you're kind of forgetting most of the stuff that came before, but like up until, until a little buffer zone. So whatever your choice of J is, right, you get a functor from the category of indexed chain complexes into itself, right, that just localizes. And you have a natural transformation. It's the unit of an adjunction, actually, which does what you would think it does, right? Which it just kills off exactly the things that you need to kill off in order for it to be localized, right? So that's what I mean by localization. Again, it doesn't coincide with the usual homotopy theoretic notion of localization. Okay.
Could you answer a question for me real quick?
Sure.
What do these long equal signs mean?
They're just equal signs. I just wanted them to be nice squares because I'm going to put them together in the end. Yeah.
Okay, thank you.
Yeah. Yeah, so that's what I mean by localization. So the point is, right, these J's parameterize how much information you're forgetting at each length scale. So the comparison, right, I had a square like this before, right? And you put this square right next to this square, right, where we're kind of like fudging the difference between chain complexes and simplicial sets. I mean, they're definitely like different categories, but for our purposes, we can kind of fudge the difference. And so we put them together and we have this, right? So along the top row, right, you get the magnitude complex, you localize, and then you apply homology afterwards. That's magnitude homology. Along the bottom row, right, that's persistent homology, right, after you take homology. Right? And so if you kind of turn this into, right, right, so this, yeah, so that becomes this, but let me just say what I mean by this terminology. This is actually like, I wanted to have a slide on kind of nomenclature, but this is like probably more for myself than it is for you, because I'm really a stickler for having like nomenclature that makes sense, and is, yeah. So we have the LP complex, NP, right? And so when P equals, I mean, this is the story that you already know. For any choice of J, any kind of sensible choice of J, we have the J localized LP complex, right? And so when we take the minimal such choice, we can call it unlocalized, right? Or a kind of like global, right? If we take the maximal choice, like we did for magnitude homology, right, we could call it localized, or the localized LP complex, right? If we want to be more specific, I guess you could call it J localized, right? So once you take the homology afterwards, right, for any P and for the minimal J, call it global LP homology, right? You call it LP, local LP homology for maximal J, right? So persistent homology is global L infinity homology, and magnitude homology is local L1 homology, right? And remember, according to this, right, this gives you a natural transformation from global to local, right? So you have a natural transformation from global homology to local homology. and you have a natural transformation from from L1 homology to L infinity homology, right? So that gives you this diagram where you have persistent homology on one vertex and magnitude homology at the other. And so this is kind of like the relationship between them. Okay, so are there any questions so far? So this is basically it for like the theoretical grounding that connects these two together and kind of tells you how these arise as like instances of the same basic construction.
Can you go back a slide to the map of the, there? I wanted to look at that just a little bit to understand it. So the arrows of the natural transformations go the opposite directions.
Mm-hmm.
Okay, thanks.
Mm-hmm. Yeah, I mean, what would be really nice if there were, you know, because these go in the opposite directions, right? You don't get like a direct comparison between persistent and magnitude homology, but yeah, it would have been nice if it were the case. But.
Do you have algorithms for either global L1 or local L infinity?
No, I don't. So no, I don't. No. I was thinking about trying to give you even a vague answer about you know, promising directions, but that's something that I was planning to maybe think about, but it was on the back burner. Yeah. But that's an interesting question. I encourage people to pursue. Okay, so one kind of payoff of having this theoretical backing is not just in kind of explaining the existence or usefulness of these tools and the connection between them. It also kind of naturally suggests like different ways you might want to apply this outwards. Now these aren't, right? These aren't like at least I don't think these aren't like amazingly like these aren't like heavy duty applications, but I thought they were kind of like, I don't know, nice lightweight applications, but maybe there's a way to take them further, right? So so persistent homology is an indicator of the failure of a metric space to be an ultrametric space. Okay. Right, and then so I'll say more about all of these in a little bit. Local LP homology so we're assuming that P is like close to 1 in this case, but local LP homology measures failure of approximate collinearity. So remember that local L1 homology, i.e. magnitude homology, measures failure of collinearity of 2 points, of triples of points, right? So we just kind of like smear that out a little bit. And if you equip an automaton with a notion of cost for its transitions between states, then you're able to, I can say that a little bit about that later, but you can just convert it into like a non-symmetric metric space, and then you can apply magnitude homology to it. And then you get some statement about like cost primitive pairs of states. Okay. Wait, this must be, wait, what happened to my slide about that? Okay. This is a technical issue. Okay, I'll just say, so luckily this happened to the least heavyweight application. Okay, I'll just say what I mean by this statement here. An ultrametric space is one in which the L infinity triangle inequality holds, right? So It turns out that in an ultrametric space, all the components of the Vietoris-Rips complex are contractible, right? All the connected components are contractible, right? And so if you have persistent homology, if you take the persistent homology of it, it's got to be trivial, right? For n greater than 0, which means that if you have non-trivial persistent homology, then it can't be an ultrametric space. I mean, it's not a hard proof. Yeah. Okay, so the second application direction, right? So I hinted about this earlier, right? When I said that the first magnitude homology group at scale R is freely generated by pairs of points that satisfy this condition, right? So that's this, right? It's freely generated by ordered pairs of points such that the distance between them is exactly R, and there's no point between them that is strictly interpolating. Okay. So we can kind of relax this notion a little bit, and we can say that a point C P interpolates between 2 points, right, when it satisfies this condition, right? So essentially what this is doing is, whereas when P equals 1, for a point to be interpolating, it needs to be strictly on the line segment between the metric line segment between these 2 points. You're now allowing it to be like slightly off the lines, the straight line segment between these 2 points. If P is like slightly greater than 1, okay? And so as you increase P, right, you're making it looser, and you're making this condition looser and looser. And so if a point P is like considered like loosely interpolating for a value of P, right, then for a greater value of P, then it should still be considered interpolating because the condition to be interpolating is looser. Okay. So the exact same proof that Leinster and Schulman give for this result actually applies for any P between 1 and infinity. In this case, it actually has to be a strict metric space. Okay, so the first local LP homology is freely generated by ordered pairs of points such that their distance is exactly equal to R, and there is no P interpolating point between A and B. Okay? So it's exactly the analog of the result for P equals 1, and exactly the same proof just goes through. And then you could maybe imagine doing something like this, where, okay, well, if you fix a pair of points A and B, right, you can say, okay, well, are there collinear points between them? Or are there approximately collinear points between them? And how collinear are they? Well, given A and B, you could take the infimum of the values of P for which first local LP homology is trivial, or that pair represents 0 in first local LP homology, right? And so yeah, I mean, the lower P is, right, you know, the better approximation you get to like a point actually being collinear, right? So yeah, so that's it for approximate collinearity. Are there any questions about this? Okay, and then yeah, I wanted to talk about this magnitude homology applied to automata equipped with costs. Okay, so to talk about magnitude, talk about automata from kind of a categorical perspective, we think about a monoid, right? And we can think of it as kind of like the free monoid on a set of letters, right? Where the operation is just concatenation, as an example, right? And so you can take the power set of that monoid, and it has a quantile structure, right? It has a monoidal, it has a multiplication where given any two subsets of the monoid, you just mash them together using the monoid multiplication that you're given, right? This has a unit, it's perfectly well behaved. And so an automaton with inputs from M, right, is a category, is an enriched category enriched in the power set of M, right? So we can think of it as like the vertices are the states, right? And then the hom object, right? So the hom between A and B, right, is the subset of M that takes you from state A to state B, right? So you might say, okay, I have an automaton. I also have a notion of what it would cost me to enact each transition, right? So we can ask for a cost function, right? So and for it to be sensible, right, you can ask for it to be monoidal or lax monoidal, right? It just means that the cost of enacting two separate transitions is at least as great as the cost of enacting them like together, like one after the other, right? With the sum of the cost of, yeah. And the cost of enacting the the unit transition, right? So doing nothing should cost 0, right? Which is definitely sensible, right? So this induces a cost function, right, on the power set of M, right, where you just take the infimum of the costs, right? So the cheapest element of here. Then, since each automaton, right, is a category enriched in P of M, right, in the power set of the monoid, and this is a monoidal functor, right, or a lax monoidal functor given, depending on what your C is, you get an induced R category, right, which is essentially a metric space. So it's a Lavier metric space for those of you who are familiar with that, right? And what the distances represent are the cheapest costs of going from one state to the other, right? So we can say that two states, right, A and B, are cost primitive, right, if there is no state for which you could kind of make a pit stop at that intermediate state and still preserve the cost of going from the original A to B, right? So like making a pit stop anywhere else would strictly increase the cost. So there, we need to make the restriction that this resulting like Lavier metric space is strict, so they can't be like distinct pairs of points at distance 0, which is a real restriction. And then you can just straight up apply the magnitude homology result, right? Because this is a metric space. And so if a pair of states is a generator of first magnitude homology at some length scale, right, it means that there's at least one, right? It means that it's cost primitive, right? Which means that there's at least one transition taking A to B, which cannot occur as a composite of state, as a composite of transitions that take you to some other state, right? And it's strictly less than the cost of such composite transitions, right? And then assuming some mild conditions, right, the converse is true, right? So if there's at least one transition that takes you from A to B that costs less than the cost of all possible composite transitions from A to B, then the pair A, B is cost primitive and a generator of first magnitude homology. Okay. So I think this is it. Yeah, and so I have a list of like references. Maybe this is, yeah, but yeah, you could look at the references at the back here, and yeah, but yeah, that's it. Thanks for listening.
Thank you.
Thank you. We can do it. It's hard to clap, but we can do what we can.
I'm not sure if I should stop sharing screen or if there
No,
are.
that's fine. Keep your screen shared. Are there any questions? I was going to ask one. It's a practical question.
Mhm.
How big does P have to be? Right. You set P by the noise in your data, right? Is that correct? So if
Right.
you know that there's intrinsic noise in your data, you don't really have to take P to infinity. You can take P to just be big enough. Does that translate one to one? Is it?
Are you talking about?
I'm talking about the local the L infinity homology, right? You don't really have to take P to infinity numerically,
Mhm.
right? If I were doing it numerically, how would I implement it numerically? I'm not really going to take P to infinity, right?
Well, let's see.
I mean, I understand. I could do it I can just find the maximum. But what I mean is, suppose I wanted to do something that was softer. Could I do it for finite P and make P large enough based on the noise in my data, the intrinsic noise in the data?
The thing about having finite P is that then you start caring about like the order in which those tuples appear, the points appear in the tuple. So
I
for
see.
example, yeah. So for example, in L1 homology, it like matters a lot what the orders of points of the tuple are. That just the fact that it doesn't really matter for persistent homology happens to be due to number one, because your distances are symmetric, but also number two, you're just taking the max.
Right.
Yeah. Actually, I should think about that a little bit. But that's
Because I'm just wondering if there's a whole if there's a whole family of homologies you could use in between, right?
yeah. So that's something that this application is kind of hinting at, right? So this is saying, well, you don't have to use
Right.
magnitude homology, which is like very on the nose. You could kind of like blur the P a little bit.
That's right. So I guess my question is could you give some, if suppose I had an error that I was willing to accept,
Mhm.
right? You know, what's the right word? A confidence level, right?
Mhm.
Could you turn this into a statistical question? How big P has to be?
So this is an extremely salient question, and one that I haven't had a chance to work out yet. So for example, one thing you could wonder is, let's see, right, there's a few ways you could kind of wonder about that question entering into practicality, right? So if you pick a different kind of J, right? Like, so remember when I said, okay, well, you could say, you don't have to make the J exactly maximal, but you could just say, okay, well, it gives you everything from 0, r minus epsilon, where now like you're not forgetting everything, but just kind of like like a band, right? You're keeping
Yes.
a band. The problem with this is that it's hard to interpret what you're getting. Like you could do the well, I'm not sure what the mechanics of the computation would be, like what the runtime of it would be. But like theoretically, you could do the computation and you're going to get something, but it's kind of hard to interpret, right? For because as soon as you let as soon as the band of things that you remember is like of non-zero thickness, you could have like composed things, and so you can have things. You could start remembering things that like kind of go outside the band, but like by stepping small steps at a time. I don't know if this makes sense.
Not to me, but I'm simple. So
Like I wish I had a board, but
I mean, you could. I see. You don't. There. You can screen share a whiteboard if you have a way of drawing.
okay, let me. Oh, great, awesome. Okay, so let's say sorry. Wait. So say this is some R, right?
Okay.
And yeah, this is some like R minus epsilon.
Yep.
This is like epsilon. Okay. Well, the reason that the proof of the result for a first magnitude homology works is that whenever you apply the face map to a two simplex and you get anything even slightly less, it just kills it. It just because you forget everything at distance scales lower, right? But now if you're allowed to keep this guy as well as this guy, right? Your first magnitude homology groups are no longer freely generated, right?
I see. I see.
Yeah. So now there's going to be like a very complicated relationship between like different pairs of points, and like as long as you're stepping between like, as long as you're like, so this is like, call this B, right, and call this point A, right, and then let's say this is like B1 and B2, and then you just, right, and then you have like, you know, some large B that's like very far away from your original B, but as long as you stepped epsilon at a time, for example, and then like each of these lengths are like R minus epsilon, right?
Yeah, I see.
Yeah. So yeah, so that's why it would be like pretty hard to interpret the results in a way that would make that would be useful
For trying to understand the bounds on.
Yeah, for trying to understand what it says about like the distances between your pairs of points, or yeah.
Okay.
Can I ask a question?
Mm-hmm.
So p equals 1 and p equals infinity are special values. Maybe this is related to Randy's. Are there any other special p's? I mean, I'm thinking naively, like an analysis where p equals 2 is the self-dual place. I don't know if there's like some kind of multiplication between, you know, the p case and the p prime case, where usually 1 over p plus 1 over p prime is 1.
Mm-hmm.
Like an analysis where you have the dual LP norms. But maybe that doesn't apply anywhere here. I'm just wondering if there's any special values of p sort of related to Randy's question, I guess, like what is there, how big should you take P, or is there some special P like P equals 2?
Right. So nothing that I've seen in my kind of categorical investigations have suggested that there's a special value of P that's like as well behaved as you see for like L2 spaces in analysis. But that might just be because I haven't found the right way of looking at it from the categorical point of view, right? It's also the case that like it's sometimes just hard to port over concepts, like translate between analysis and category theory in fruitful ways. So that's
I was thinking of some kind of tensor product where you naturally be multiplying things. I'm not sure what you'd be multiplying.
Yeah. So that I'm not sure myself either. Yeah. But I mean, I don't know.
It's a naive question. It's not meant to be anything.
Well, I mean, lots of insights I think arise that way, right? So, but yeah, that's a good question, though. Yeah. Sorry, someone just gave me a chat. Oh, okay, never mind. Cool. Yeah. Are there any other questions?
Hello?
Hi. Yeah.
I have a question. So suppose you did this with a very large P.
Mm-hmm.
Sort of like Vietoris-Rips, except there would be restrictions on the shapes of the simplices, not just their inter-vertex distances.
Mm-hmm. So are you asking like what that would mean, like what we would get, or?
Yeah, I'm not sure all that specifically what I'm asking, but I'm thinking that maybe you could, that by using a very large P, that you would select simplices that are very sort of round, or but maybe very flat or something like that.
Yeah. Yeah, I don't know. I'm kind of doubtful, right? Because as soon as you, right, like it kind of starts converging to like numerically to like the L infinity case, like pretty quickly, right? For even like moderately high values of P, right? So if you start using really large values of P, you get stuff that's like numerically basically the same as the Vietoris-Rips complex, but it's like more complicated computationally to deal with. So I'm not sure what exactly you get. So one shortcoming with my work, like the way the things that I've said, is one of like interpretability, right? So I've just like said, okay, well, here's like a whole new world of like different like homology, different sorts of homologies you could take, right? But like even when it comes to persistent homology, right, or magnitude homology, like the higher homology like classes, right, in these like even very well-known cases are like hard to interpret in general, and like even like there's no uniform kind of meaning for them. It's like it tends to be pretty domain specific, right? And for these kind of less well-known or like actually just straight up very like, completely new homologies, right, it's like very unclear what they would be saying about the distances involved. So that's certainly like a shortcoming with this material, I would say. And I would be very interested to see if people want to push in that direction and say, okay, like, well, this kind of looks like it would be saying something, right? Like I would highly encourage people to like, if that's a question that you're interested in, if you want to work it out.
Other questions? Well, that was great. Thank you. Let's